So today I want to talk to you a little bit about lesson 5.3. This is on the derivatives of trigonometric functions. And we're going to spend a little bit of time today reviewing trig functions themselves. Very little time, since we've done that already once this year. But these are not trivial in the sense of being much more difficult than the polynomials. Right? These are not polynomial derivatives, which are really all of the derivatives we looked up to this point. So that means that to a great degree we can't use this relationship. We have to come up with a different relationship to use. So let's go ahead and take a look. The first thing I want to do is just focus on the function sine of x and recall for you what the graph of sine of x looks like. And we're actually going to go ahead and make use of some analytical properties of the derivative. So recall that the sine function has a period of 2 pi. And so we can look at the function that does something like this, where we have an amplitude of +1, and we go down as far as -1 as well. And so we can take a look at what's going on with the derivative here by thinking about the slope. So let's now think about what the derivative of the function sine of x might look like. And I think we've done this in class already when we first introduced these functions, but again, we'll look over the interval from 0 to 2 pi, and we're not going to worry so much about the amplitude here because we don't necessarily have enough detail to figure out exactly what the amplitudes are. But if you think about it, in this region right here, the derivative is positive, and the derivative remains positive as we move along. However, it gets less and less positive. And at this point right here, the derivative itself, if we think about that tangent line, this is going to have a horizontal tangent line here. So this function is actually decreasing from the interval from 0 to pi over 2. And so at pi over 2, we have a derivative of 0. This function is decreasing on its way to pi over 2. And if we think now the derivative is actually negative, so this function will go down into the negatives until we hit 3 pi over 2. And at 3 pi over 2 we will have a minimum once again. So at 3 pi over 2 we will cross the origin again. In fact, you can see that this is the steepest part of the curve right here. This is the steepest portion of our function, and so that will be where the derivative is the minimum. So this will come down like this and come back up, something along those lines. And from 3 pi over 2 up until 2 pi, we have positive derivatives that are getting steeper and steeper. So these functions are going to get steeper and steeper until we end up something like this. So the derivative of the sine of x is a function that looks something like this. And when we're thinking about trigonometric functions, we see something like this, we should immediately think cosine. This could be the cosine of x. And again, because we didn't do anything very quantitatively, this might be some number times cosine of x. But it certainly looks as though it's that cosine of x function. Well, let's explore this in another way. Let's see if we can figure out how to get a new page going here. There we go. So let's see if we can work out what this derivative actually is. So let's do this analytically. In other words, let's use some algebraic or analytic methods to figure this out. So we would like to figure out what the derivative of the sine of x is. We can use the fact that the derivative of any function is defined as the limit of the secant slopes. So we can look at this as the limit as h goes to 0 of sine of x plus h minus sine of x divided by h. And we can evaluate this limit. It's not an extremely easy limit to evaluate But one of the things we can do is we can use an angle sum formula here to simplify this particular expression and allow us to express this now just in terms of single arguments. So we have the limit as h goes to 0 of the sine of x, the cosine of h, plus the cosine of x, sine of h, minus the sine of x, all over h. So we can work to simplify this a little bit further now. This is going to be something that we can group some items together and break things up. Again, we're looking as the difference between the 2 points we're computing the slope for approaches 0. Notice that I have two terms here. Notice I have two terms here. This term and this term both depend on the sine of x. So what I can do is I can go through and collect these two terms together. I have a sine of x cosine of h term, and I have a minus sine of x term. Those are all over h. Plus, then I will have a second term, the limit as h goes to 0 of cosine of x sine of h divided by h. Just a few more steps here. If I factor a cosine of h, or rather if I factor a sine of x out of both sides here, we can end up with the limit as h goes to 0 of sine of x times the cosine of h minus 1, all divided by h, plus the limit as h goes to 0 of cosine of x times the sine of h over h. And we can look at both of these expressions here. Both of these pieces have some h dependence in the numerator. If you explore this ratio cosine of h divided by h, and you look at cosine of h minus 1, as h goes to 0, this expression actually goes to 0. You can verify this on your calculator or explore this numerically to figure out what this limit is. So the first portion of this object goes to 0. Likewise, we've explored this limit before when we were introducing limits, and you can graph this, or you can look at this numerically. But one of the things that you should remember is that this is equal to 1. This particular limit here gives us a value of 1, and therefore the only thing that's left is cosine of x. And so we can see that numerical factor that we weren't sure of what that would be simply ends up being 1, and now we have a statement of our derivative here. We can say that the derivative of the sine of x is equal to cosine of x. We can go through and do similar arguments. I'm not going to address all of these at once, but we can take a look at what the derivative, for example, of the cosine of x is, and we can graphically kind of sketch out what this looks like. And it looks like a reflected sine graph, and in fact that is the derivative of that sine function and the derivative here of the cosine function. Notice that we have a negative sign here. This is something that we're going to see in general as we go through, that the derivative of a trig function that starts with the letter C is always negative. So this is a very useful tool, because as we go through and do all these trig functions, it gets rather difficult to remember what the actual values are. So now we have the derivatives of sine and cosine. The next logical place for us to go is to think about, well, what might the derivative of tangent be? And to do the derivative of tangent, we can set up a relationship here that actually makes use of some information that we have been working with already. So let's take a look at what the derivative of tangent might look like. We could look at this in terms of limits, and we could go back and use the basic definition of a derivative. What I'm going to go ahead and do rather is look at the derivative as the derivative of tangent as the ratio of the sine of x and cosine of x. And we're going to compute the derivative here using the quotient rule. So good review of the quotient rule. And what that tells us is that our result is going to be the function in the denominator, which is the cosine of x, times the derivative of the function in the numerator, which is the sine of x, minus the numerator function, sine of x, times the derivative of the denominator function, which is cosine of x, all divided by that denominator function squared. And you can see that we'll be able to compute this trig function derivative because we've already figured out what the derivatives of sine and cosine are. So this first term in the numerator, cosine of x times the derivative of the sine of x, is simply going to be cosine x times cosine x, since the derivative of sine of x is cosine x. And for the second term, we have the derivative of cosine of x times sine of x. The derivative of cosine of x, we can see right above there, is minus sine of x. And this, of course, is all divided by cosine squared of x. So if we go through now and we evaluate this, recall we're looking at the derivative of the tangent function, and at the moment what we have is we have cosine squared x minus a minus or plus sine squared x, all divided by cosine squared x. Well, the numerator is an identity. Hopefully you remember that most important identity, the Pythagorean identity, gives us a value of 1. Sine squared plus cosine squared is always 1. So this simplifies down to 1 over the cosine squared of x. We can rewrite that reciprocal trig function as the secant squared of x. So we have another relationship, another derivative that we have worked out now. The derivative of tangent of x is the secant squared of x. And very important relationship there. Well, we can continue to build more derivative functions by going through. I'm going to do one more example, and then I'm going to ask you to do the remaining examples. Let's take a look at the derivative of secant of x. Secant of x, recall, is the reciprocal of cosine, so I could think of this as the derivative of 1 over cosine of x, and then we can go through and use the quotient rule again. So the quotient rule would say that this is the denominator function, cosine of x, times the derivative of the numerator, which in this case is just 1, minus 1 times the derivative of the denominator function, which is cosine of x, all divided by cosine squared of x. And this simplifies out quite easily because we have so many things that simplify nicely. The derivative of 1, since that is a constant, is 0. The derivative of cosine of x is minus sine. When we couple that with the minus 1 here, we end up with a positive sine of x divided by cosine squared of x. We can break this up. The denominator is really cosine of x times cosine of x. Sine over x times cosine of x is tangent of x, and cosine of x in the denominator is a secant of x. So again, we have another derivative here. We can say that the derivative of the secant of x is tangent of x times secant of x. For class tomorrow, I would like you to have the following two derivatives worked out. They're basically the same process, but it will give you a little bit more experience in seeing how these things go together and working with the trig functions we've been working with. Please find for me the derivative of cotangent of x and the derivative of cosecant of x.